Good morning, students. Myself, Vijay Shankar from ECT Department, Chipral Engineering College. So today we are going to discuss about some more examples in the Fourier series. In the yesterday class, we've seen some examples in the Fourier series. Now, some another examples in the Fourier series. To obtain the polar Fourier series of the signal. So already we find the Fourier series, trigonometric Fourier series of the signal exponentially decaying function with a period of 0 to 0.5. Now you can find out for the same example polar or compact trigonometric Fourier series. Compact trigonometric Fourier series. We got A0 is equal to 0.7869 and AN is equal to A0 is equal to 0.7869 and A of K, or it is A of K is equal to is a 1.576 whole divided by 1 plus 4 pi k whole square. One by 1 plus 0.32 pi k whole divided by 1 plus 4 pi k whole square. 4 pi k whole square. So what is a compact trigonometric Fourier series or the polar Fourier series? Is x of k is the other x of t is equal to is a naught of a of 0 plus sum of k equal to 1 to infinite. You get here the a of k into cos k omega naught t minus tan inverse b of k by a of k. This is a d of k, my dear friends. A d of k, it is a d of 0. Not the a of 0, it is a d of 0. D of 0 and the a of 0, both are the same. The d of 0 and the a of 0. And the d of k, the d of k is equal to the under root of a of k whole square. See the 1.57 whole square by 1 plus 4 pi k square whole square plus 6.32 pi k whole square whole divided by 1 plus 4 pi k square whole square. And simplify here, denominator is the same, 1 plus 4 pi k square whole square under root, and in the numerator 1 plus 1.576 whole square plus 6.32 pi k whole square. And now you can 1.576 whole square you can take as a common. The 4 times it becomes of 6.32 whole square. So 1.576 whole square, you can take the one common is here, the 1 plus 4 pi k whole square. The 4 pi k whole square. And already we have here the 4 pi, 1 plus 4 pi k whole square and whole square in the denominator. It's a both are get cancelled here. One term. Then the pi of k, here the cos k omega naught t minus pi of k here. The pi of k is nothing but the tan inverse b of k pi a of k, b of n pi a n. What is the bn here? 6.32 pi k whole divided by this one and here 1.76. So the 6.32 pi k whole divided by, and denominator is a 1.576. 1.576. So this is a 1.576. So 4 times it will get. So minus tan inverse 4 pi k. The denominator both are the same. So it get cancelled. Minus tan inverse 4 pi k here. Cos k omega naught t. And this function is a d of k. In this d of k, you can see here, one term is get cancelled. After that, we have only the under root of, not the under root of 1.576 whole square, and here it is a 1 plus 4 pi, the under root is there. This one. Because it's a square is a one term only, they get cancelled, and we have under root. So x of t is equal to d of 0 and d of k here. Got it, my dear students? So the polar form, the x of t is equal to d of 0 plus sum of k equal to 1 to infinite the d of k cos k omega naught t minus pi of k. The d of k is the square root of the magnitude, simply saying the magnitude is under root of d of k square plus b of k square. And the d of 0 is same as the a of 0. That's a 0.7869. For the same function, you can find out the exponential Fourier series also. You find the trigonometric Fourier series for the same example, and polar Fourier series for the same example, and the exponential Fourier series. In the exponential Fourier series, we have the coefficient x of k is equal to, the formula is 1 by d, the integral 0 to t. Actually, it is a integral of t on the x of t e power minus jk omega naught t dt. So what is the range here? The 0 to 0.5. The range is 0 to 0.5, and the signal is e power minus t. So x of t is equal to e power minus t, and the range is 0 to 0.5. And in that, the omega is omega naught is equal to 2 pi by t. The t is 0.5. The 0.5 will get the 2 pi by t, and the 0.5. 0.5 means 1 by 2. You will get in the numerator, you will get the 4 pi. So x of k is equal to 1 by t. The t is 0.5. The range is integral 0 to 0.5. The signal is e power minus t. And e power minus jk omega naught. What is omega naught? We got 4 pi. So 4 pi into t is also there, my reference here. Okay. Then 1 by 0.5 means a 2. The integral 0 to 0.5 e power. Both the bases are the same here. Add the power e power minus. You can take the minus as a common. 1 plus jk 4 pi. The t is also there here. 3 into dt. The integral of e power minus t is same as e power minus of 1 plus jk omega jk 4 pi into t whole divided by the coefficient of t is 1 plus j 4 pi k, and the 2 is already there. Upper limit is a 0.5 and the lower limit is a 0. Okay, so whenever you can substitute the upper limit of 0.5, that is a 1 by 2, 1 by 2, and the 0, and the t is a 0 means e power 0. E power 0 is a value is 1. Okay. So simplify this function. Minus 2 by 1 plus j 4 pi k e power minus 1 plus j 4 pi k into 0.5 minus e power minus 0. So split this part, the two parts, e power minus 0.5 and e power minus j 2 pi k, and e power anything power the 0 is a 1. We already know the e power minus 2 pi is a 0.606, and e power j 2 pi k is always a 1, my dear students. Why it is? Cos 2 pi k into sin 2 pi k. Sin 2 pi k is a 0, and cos 2 pi is a 1. Always it is a 1 the value. So minus 2 by 1 plus j 4 pi k into 0.606 minus 1. So this value is a 1. 1 into this 0.606 and minus 1. After simplifying this, the numerator will get the 0.7869 whole divided by 1 plus j 4 pi k. Exponential Fourier series. Got it, my students? And for the same function, you can find out the magnitude and the phase plot. Magnitude and the phase plot. So what we got, the x of t is equal to, x of t is equal to, this is the synthesis equation now. In the exponential Fourier series, the two equations we have, one is analysis equation. By using the analysis equation, we find out the x of k is equal to. And the synthesis equation is x of t is equal to sum of k equal to minus infinite to infinite, x of k into e power plus jk omega. X of k is equal to the 0.7869. You can rationalize the factor, denominator having 1 plus j 4 pi k and multiplied with 1 minus j 4 pi k by 1 minus j 4 pi k. At denominator, we see here the a plus b into a minus b. It becomes of a square plus b square, a square minus b square. At that minus is becomes a plus by the j square is there. J square is equal to minus. Minus into minus is plus 1 plus 4 pi k whole square. In the numerator, 0.7869 whole multiplied with 1 minus j 4 pi k. So now, write the real term, 0.7869 is our real term. And imaginary term is a coefficient of j, 0.7869 to 4 pi k. And to find out the magnitude of x of k under root of the real square plus imaginary coefficient square. The real square here, the imaginary coefficient. Take the 0.7869 whole square and here also 0.7869 whole square. Take the common of 0.7869 whole square. And in the numerator, we have the 1 plus 4 pi k whole square. 1 plus 4 pi k only, it is a whole square minus. So the numerator having 1 and the denominator is cancelled. So 0.7869 under root of 1 plus 4 pi k whole square is a magnitude. The x of k, we got the magnitude. So the phase is imaginary coefficient. The phase, you can say the tan inverse imaginary, there's a 0.7869 into 4 pi k whole divided by the denominator is both are the same for the real and imaginary. So 0.7869. So both get cancelled. The tan inverse 4 pi k. Phase angle of x of k is equal to, it is a minus. Got it? The imaginary is a minus tan inverse 4 pi k. And the magnitude and the phase plot by taking the some values here. You substitute the 0 in the magnitude, the 0. See here, k is equal to 0. The denominator becomes 1 plus 0. The value is under root of 1 plus 0 is a 1 only. 0.7869. 0.7869. So at the value of 0, it is a 0.7869. And 1 means you can simplify, but gradually it is decreases the value here. And it is the same, the value is also here the same value, the positive value. So after they plot the graph, the magnitude becomes, the first value is a 0.7869. And for the second one, it is a gradual, it is a decreases at 1. So it's a 0.7869 whole divided by under root of 1 plus 4 pi k whole square. So first of all, if I am taking the k is equal to 0, it becomes of 0.769. For pi k, for pi whole square, and simplify this one, you'll get the 0.0624, and slowly it decreases. Okay, and in the symmetric also the same value will get at -1 also, and the +1, +2 and -2, and +3 -3 is also the same values. So the plot of the graph is towards negative expressions, and here towards the positive values. Gradually it decreases from 0 to some values of 3, and here from 0 to -3 also. Now coming to the phase plot here, when k is equal to 0, the tan inverse 0 is 0 only. Here it is a 0 value, and minus tan inverse k is equal to 1. We can get the values. Actually, it is a minus pi by 2 the pi by 2. So there is if I am taking the infinite here, minus infinite, and here the plus infinite is there. 0 is equal to 0, tan inverse 0. Minus means the minus tan inverse. Tan function is odd function. Tan of minus theta is a minus tan theta. We get the positive, and tan inverse infinite is nothing but the pi by 2. For the negative values, is a decrease is a pi by 2. See, this is a pi by 2 here. In terms of the degree, we can find out is a pi by 2, and gradually it decreases and it goes to the 0 at origin. And here its range is also minus pi by 2. Why it is a minus pi by 2? The infinite here the minus is there, minus pi by 2. So the angle is varies from minus infinite to plus infinite, plus pi by 2 to the 0, and passes to the 0, goes to the passes 0, and again it is a constant at minus pi by 2. So these are the values of radians. And k is equal to -1, k is equal to +1, k is equal to -2 and +2. They're all the radians values, and these are degree values. I'm saying the degree plus pi by 2 is a varies in between plus pi by 2 to the minus pi by 2. Got it, my students? So this is a way we can find out the any given function, the trigonometric Fourier series, and compact trigonometric Fourier series, and exponential Fourier series, and how we can find out the magnitude and the phase for the given exponential functions. Second unit to the Fourier series is completed, my students. Now we go for the second part of the second unit. Second part of the second unit is a Fourier transform. As per your syllabus, the first part of the Fourier series is completed. This is a Fourier series introduction, and some of the properties and some examples on that trigonometric Fourier series, compact trigonometric Fourier series, and the exponential Fourier series. Now we go for the second part of the second unit is a Fourier transform. Series of second part in the second unit is a Fourier transformation, my friends. See, what is a Fourier transform? See, for the periodic signals, the analysis of the periodic signals using the Fourier series, the periodic signals which extended over the interval minus infinite to infinite can be effectively represented with the help of Fourier series. So it's a very important point. Fourier series. The periodic signals which are strictly time limited can also be represented by the Fourier series. A time limited signals means it has a zero value outside the specified interval, and asymptotically time limited means as the time approaches to the infinite, the value of signals becomes zero. Such time limited signals can T0 tends to infinite, my students. See, finally we are saying that the periodic signals is for the Fourier series and Fourier transformation is for the aperiodic signal because their time period is a T tends to infinite. Such time limited signals can be more conveniently represented by the Fourier transform in the frequency domain. So the Fourier transform can also be found for periodic signals. Fourier transform can also be found for the periodic signals. It provides effective reversible transformation link between the frequency domain and the time domain representation of the signal. So how it is a Fourier transformation and inverse Fourier transformation also. But in the Fourier series, we don't have the inverse Fourier series. So in the Fourier transformation can also be found for periodic signals. It provides effective reversible transformation link between the frequency domain and the time domain representation of the signal. We have seen the previously for the non-periodic signals, T0 tends to infinite. As a period of signal, T tends to infinite, F0 is equal to 0. Therefore, the spacing between the spectral components becomes infinite, and hence the frequency spectrum appears to be continuous, whereas the periodic signals has a fixed period T0. Therefore, the frequency spectrum is discontinuous, as we have seen in the examples in the last section. See, forget about all these things, what they are saying. Simply the Fourier transformation is analyzed for the non-periodic signals also, the found for periodic signals. And Fourier series is for the periodic signals only. And it is a effective reversible transformation link between the Fourier frequency domain and the time domain function. The definition of the Fourier transformation saying that the limit let x of t be the signal, which is a function of time t, the Fourier transform of the x of p is given. The Fourier series is nothing but x of k is equal to minus. See, the x of k is equal to it because of it is a periodic signals having the 1 by t and the integral values is t. X of t is the input signal, the time domain signal, and multiplying with the exponential value, negative exponential e power j k omega naught t dt is a formula for the Fourier series. Now the Fourier transformation formula is x of omega is equal to the x of k is the Fourier series coefficient in the frequency domain, and similarly the frequency domain of the Fourier transformation is x of omega, and it is not for the periodic signals, it's a periodic signal function. So the integral start from the minus infinite to infinite. As the t tends to infinite, the x of tends to 0, the t tends to the infinite. The same signal x of t, the exponential value is e power minus j omega t dt. There is no any k value here. So Fourier transformation definition and the Fourier series definition. Fourier series definition. And this Fourier transformation having the inverse Fourier transformation also. Before going to find see the inverse Fourier transformation, and for angular frequency of omega, I can convert this angular frequency as a 2 omega. The omega is equal not to 2 omega, 2 pi f omega is equal to 2 pi f, and the d omega is equal to 2 pi into df, 2 pi into df. Now you can change this function as x of omega. That omega I can represent it as a 2 pi f is equal to integral minus infinite to infinite. But x of t is the same thing. Now I'm changing this function as e power minus j 2 pi f into t, and it's all the t functions only. You can write it as a t. The shortcut notation of the x of 2 pi f is x of f is equal to x of f is equal to integral minus infinite to infinite x of t e power minus j 2 pi f into t dt. Is in the normal frequency x of f definition of the Fourier transformation. And why I wrote the del d omega the 2 pi f into df means it's the inverse Fourier transformation. Inverse Fourier transformation saying that is x of t is equal to x of t is equal to x of t, get it is a time domain is output function, means the input function is x of omega. Previously we are using the e power minus j omega t, now it is e power plus j omega t into this function is frequency, means apply that is a d omega. This is the inverse Fourier transformation definition. So in terms of the normal frequency, the f value, the x of t is equal to here the 1 by minus j, that omega becomes 2 pi f into t, and d omega, now the d omega is 2 pi f into df. So 2 pi f into df. So here the 2 pi get cancelled. Finally, it becomes of x of t is equal to integral minus infinite to infinite x of a transformation definition in the angular frequency and the normal frequency. The Fourier transformation definition of in the angular frequency and the normal frequency. What it minus means? Here there is no negative value minus. It's a plus only, sorry. Is a plus. Negative exponential for the Fourier series only. Positive exponential for the inverse Fourier transformation. Not the Fourier series, Fourier transformation. Okay. So here the inverse Fourier transform 1 by 2 pi integral minus infinite to infinite x of omega e power plus j omega into t d omega, and now it is in the normal frequency x of t is equal to integral minus infinite. There is no 1 by 2 pi minus infinite to infinite x of f e power j 2 pi f into t df. Okay. The Fourier transform having the function x of t and x of f form a Fourier transform pair. So the x of t applying the Fourier transformation is x of f, a shortcut symbol it is, and x of f is equal to the Fourier transform of x of t or otherwise, and x of t is equal to f inverse of x of f, nothing but inverse Fourier transformation of x of f. See in the block diagram representation here, the x of t is the input signal, the time domain signal. Applying the Fourier transformation for the x of t to get the frequency domain signal is x of f, the Fourier transformation. And inverse Fourier transformation is the input is a frequency domain, here, frequency domain. Here the input is a time domain. The time domain function, the time domain. After the Fourier transformation, you can apply for the time domain. Time domain is out. Got it, madam? The next is a purpose of the Fourier transformation. For the non-periodic signals can be represented with the help of Fourier transform here. But periodic signals can be represented with the help of the Fourier series. Here the Fourier transformation is for the non-periodic signals can be represented with the help of Fourier. Non-periodic signals G naught tends to infinite as the omega naught is equal to 0. Why it is omega naught is equal to 0 means is the frequency is infinite, frequency is a 0 means so that definitely the time is infinite. Why the omega is equal to 2 pi by t minus 2. It's a formula or 2 pi f. The t tends to infinite means omega tends to the 0. As the omega is equal to 0, therefore the is a magnitude spectrum or that is a phase spectrum. The definition you can see the x of omega is equal to, and in terms of normal frequency x of f, and inverse Fourier transformation x of t, and in the normal frequency also the angular frequency and the normal frequency expressions. The Fourier transformation pair is represented as x of t is a input function applying the Fourier transformation x of omega. X of t is a input function. And here also there is some distinct conditions similar to that of Fourier series. Already we discussed in this one. The 4 Dirichlet conditions existing of the Fourier transformation also. The following conditions should be satisfied by the function x of t for the Fourier transform. The single valued property must have only the value at any time instant or the time interval. We already seen that there is no double valued here like this at the same value of the t, and single valued of the t only at t is equal to 1, we have only the value is 1. The t is equal to 0 and the t is equal to 2, let us assume. If the t is equal to 0 and the t is equal to 1 and the t is equal to 2, at 1 there is a double value here. Means it satisfies the condition only for the single valid property. Single valid property, the x of t must have only the value at any time instant for the finite time interval t. And finite discontinuities. Here also the finite discontinuities. X of t should have at most finite number of discontinuities for the interval of t. Finite peaks. Here also x of t should have the finite number of maxima and minima over the time interval of t. And it is also absolutely integrable. Is less than the infinite. These conditions are sufficient but not absolutely integrable and the single valid property. Got it? Coming to the properties. Okay. Here also the same. Of the properties. Properties is a linearity property we already seen in the Fourier series. Here also the linearity property is there. And the second property is a time shift property. In the Fourier series also we see in the time shift property and frequency shift property. In the Fourier series also we have the frequency shift property. And time scaling property in the Fourier series is also we have the Fourier time scaling. Differentiation. Time differentiation. Here, time differentiation is there and the frequency differentiation is also there. The Fourier series, we have only the time differentiation. There is no any frequency differentiation for the Fourier series. This is an extra property we have in the Fourier transformation. And convolution property. There is also the Fourier series, we discussed the convolution property and we derived the convolution in the time domain. Convolution in time domain means time is convolution, the frequency is the product. Okay, there is no any integration property in the Fourier series. Frequency differentiation is not there in the Fourier series and the integration property is also not there in the Fourier series. Remaining all the properties are there. That is the 6 properties what we discussed in the Fourier transformation also. Modulation property is there in the Fourier series. Means modulation means multiplication in time. Multiplication in time. Convolution in the frequency. Multiplication in time means the convolution in the frequency. Got it? Using the Fourier transformation definition, we are deriving here. There, by using the definition of the Fourier transformation, the definition means the exponential Fourier series, that to analysis equation. And duality property is a third different property is there in the Fourier transformation. This property is not there in the Fourier series. Symmetry properties. Symmetry properties also we discussed in the Fourier series. So these are, and Parseval's theorem. What are the different properties out of the 9? The same there. 10th property, 11, 12. The 3 is, one is a frequency differentiation, and the other one is integration property, and the third one is a duality property. Okay. The 9 properties, what we already discussed in the Fourier series, is the same. The time differentiation, convolution, modulation, and the symmetry, Parseval's theorem. Only the 3 different is there. That is duality property, integration property, and frequency differentiation. So okay. So we listen carefully, my students, and this practice all the properties what we discussed in the Fourier series and Fourier transformation also. Okay.